Now I want to talk about the fact that the design of these flocculators really changes dramatically depending on what the flow is that you're trying to treat. And this is an evolution that has taken us many years to figure out how this evolves. So this first one is a tiny flocculator that would treat between half a liter per second and maybe up to 20 liters per second. We're not actually sure where that top boundary is. And this flocculator has flow that at the big scale, the flow is going down one channel and then up the next channel. So you see that in this picture here, flow is going down one channel and then across in between and then up the next channel. And then over to the next channel and down. So it's up and down, up and down, up and down. So that's vertical. That's the first word, it's vertical. And the second word, it's horizontal. At the smaller scale, as it's going down, it's going back and forth and back and forth and back and forth, and then over to the next channel, and then back and forth as it goes up. Got it? So it's vertical, and then fine scale, back and forth, so horizontal. So that's a vertical horizontal flocculator. These will be used for small plants. Next one is the kind of flocculators that we've been building lots of, and I call these horizontal vertical because at the big scale, it's horizontal flow as the flow goes down one channel and back the next. And at the smaller scale, it's going up and down around the baffles. Questions about that? So this is the design that we use for flows maybe between 20 and 200 liters per second. And I always think it's fun to see when you have two technologies and they both work and they're both like competing at a crossover point. Here I specified that the small ones go up to 20 and then this one drops down to 20, but that 20 is pretty arbitrary. There's nothing about physics that says exactly where that transition has to happen. And so this is a case where a combination of economics and constructability will create a little tug of war between these two technologies, and we'll see which one actually is best up to what flow rate. And it's possible that the transition is at 5 liters per second or at 30 liters per second, and there'll be a little internal fight between these two designs to see who wins. Okay. As we go bigger, it changes again. And this is now the flocculator that you're designing for your design challenge. Although you're designing one of these, this is some students previously designed 10 flocculators acting in parallel, each of them treating, I'm trying to figure out, is that 20 liters per second total? And now I don't remember. I think that was 20 kiloliters per second total, which is a big number. 20,000 liters per second. This was for a design for a plant for Los Angeles that we were playing with. So in this flow, or in this type of flocculator, the flow is all horizontal. It's horizontal down the length of a channel, and it's horizontal back and forth around the baffles as it goes down the channel. Those three different designs are all done to keep like scales of things reasonable, and to think about how a human is going to fabricate it, and to not end up with ridiculously deep tanks, or ridiculously shallow tanks. So that's what was driving the geometry for those three different approaches to designing hydraulic flocculators. Goodness, there's a typo on this, but downstream water level plus head loss gives the upstream water level. So this is about what's setting the water level in the flocculator. And the important thing is to recognize that there's a sedimentation tank downstream, and its water level is actually set by a weir at its outlet. And there's hardly any head loss through a sedimentation tank. About 5 centimeters is what we'll end up using. And so it's the sedimentation tank that sets the water level at the downstream end of the flocculator. And then there's the head loss through the flocculator. That means that the water level, as you go upstream in the flocculator, the water level has to increase. We're going opposite the direction of flow, so we have to have more and more potential energy available there to drive because of the losses around each baffle. You might be wondering, well, do I have to have my water level at the effluent of my flocculator set by the sed tank? Could I have it just be higher? Why couldn't I have a higher flocculator and then dump the water into the sed tank?
All the flocks up.
It would break them all up.
Record.
Yes. You just learned something really important. You can't have a waterfall and expect flocks to survive. You have to treat, once you've flocculated water, you have to treat it very, very carefully. And it only takes one little bad engineering design to break up all those flocks again. It wouldn't even require a waterfall. It could even just be a place where the velocity was extra high, where there was a little bit of head loss. So got to treat, oh, this might be helpful to you. I think in your design challenge, you're going to calculate how much head loss there is going around each baffle. And it's a tiny bit of head loss. And that's enough energy to make the flocks. And if you had much more energy, it would break the flocks. So that little head loss is an indication of how tiny the waterfall could be before there'd be a problem. So this is a side view of a flocculator showing a water level, and you'll do the same thing with your flocculator, showing that the water level is dropping as you go through the flocculator. I could have been more careful and thought about, maybe the water level between baffles is actually flat, but I was too lazy to draw that. So if you want more detail, you could think about drawing this more carefully. But the point is that there's more water in your flocculator than what you first realized. Because when you designed the residence time for the flocculator, you assumed, or we would assume, that the water depth of the sed tank inlet is what's setting the water level in the flocculator. And we use that to calculate, or we use that to calculate the required volume. And we don't take into account the fact that there's some extra volume due to head loss. So we ignore that extra volume when we're designing the flocculator. And what it does is it makes our final design just a tiny bit better than what we were expecting, because there's a little bit more residence time, there's a little more space for water to be deforming. And so it makes it work a little bit better than what we had designed for. That makes it simple. This is a flocculator design that wasn't created by Agua Clara, although we have made our fair share of mistakes too. So this is another group that made a mistake. You see what happened in this flocculator. I'm sorry, the image isn't any better. Can you describe what caused this to show up in their design? Yeah, their H/S ratio is too small. It was actually less than 2. And so there's no overlap. We wanted something like this where the water was forced to go around the bend, and instead we have this. And now, even though you might really like it if the water would go around those bends, the water isn't listening to us. The water is doing what's easiest. And the easiest thing to do is to go straight down that channel, right down the middle. And it happily does this. And that is a terrible flocculator. Okay, now you won't make that mistake, right? You will make sure that when you design a flocculator, the water has to follow the path that you want it to follow. Here's a view of another flocculator to show that there are many ways of making this. This is another horizontal flow flocculator. So we're looking down on the top of this relatively small thing. You can see those are boards. So those boards are probably 3/4 of an inch thick. And you can see that they have a path so that the water has to go around one set of boards end to end. See that path? So this is the same thing that you're designing for your design challenge, except your design challenge is at a much bigger scale. Okay, so now we're at the fun part. We're going to do a little exercise where I want you to think about what you've been learning about flocculators, and I want you to reflect on how many expansions are there in parallel in the designs that we've been talking about. So that's the first question. How many flow expansions are there in parallel? And then I want you to think about, well, why don't we try having multiple flow expansions in parallel, meaning that the water has an option of going through multiple paths. Each path has its own flow expansion and contraction, or contraction and expansion, but there are many paths in parallel. And I want you to think about what happens if you have many paths in parallel. I want you to think about how you might invent a flocculator that would use that idea of many paths in parallel. So how would you make it? And what would it look like? And then what insight do you have about if you have many expansions in parallel, what happens to the distance between the expansions? So how closely spaced do you have to have the flow expansions as you increase the number of expansions in parallel? Wow, so that might be a big chunk to think about.